So thank you for the invitation. Well, I think everything I want to tell you is contained in the title. Well, I mean the keywords. I will probably not have time to speak about everything, so we try to. We are asked by Gaz de France and then GDF Suez after the two companies merged to develop a hedging method based on the conditional value at risk, including some theoretical approach and its numerical implementation. So in some sense I will tell you what happened. It was 2 or 3 years ago, and the paper has been published in Mathematical Finance ever since, so it's not really a fresh material. It's a 1 or 2 or 3 years old material, but well, I have never the opportunity to talk about it in an audience like today. So why risk hedging? So this is a very fast slide. You know that in a complete market you have no residual risk because you can duplicate or replicate any payoff or contingent claim capital L. It's just a fixed notation. But of course we know that most markets are not complete because of stochastic volatility, because of peaks of price on the spot market of electricity, for example, because of the discrete time nature of gas market, where the time scale is larger than on the usual markets on stocks or electricity, etc. Because of climate randomness, of course, and we'll come to that point later on. And more precisely, because, for example, in the gas market, the price of the underlyings, the future on the gas, and consequently also not only the price, but the payoff itself depends on the temperature, because you don't use as much gas when it's hot than when it's cold, of course. And we'll see what this payoff is later on, but you can imagine that's the consumption of gas times the difference of two prices, a regulated price between against a market price. Okay, so how to deal with the incomplete market? It's a very classical topic in mathematical finance, maybe the hugest topic since the last 20 years. So you have, of course, super hedging, specify a martingale measure using a criterion like entropy or other methods, expected utility maximization, indifference prices, etc. You can also consider some risk measure, and that's what we will do now. So you have, of course, the seminal paper by Fulmer Sunderman on quadratic risk minimization, but you can also maximize the hedging probability. You have convolution of risk measure and BSD developed by Pauline Barieux and co-authors. And maybe it's the last line that we will on which we will focus, which is the portfolio optimization using a CVaR criterion. We will not do that exactly. We will change what is the criterion and what is the constraint, but we will focus on this conditional value at risk, and this portfolio optimization using the CVaR criterion was developed by Rockefeller and Uriasef in the early 2000s. So what is the motivation? I already spoke about the motivation and the framework. So we consider a discrete time market. So it's very elementary with de-traded assets. And the incompleteness source of the market is that we have an observable source of risk, Z, which is in fact the temperature. And, but this is observable, but not really tradable. So the filtration of observable events is given by the filtration of the prices and the temperature. So the contingent claim is the loss resulting from a consumption of gas at time capital T, or possibly electricity, which is sold at a regulated price capital K, while purchased at price S of capital T. So the payoff is the difference between these two prices times the consumption. But you can imagine, as I told you, that the consumption is a decreasing function of the temperature, or even here in a fine decreasing function of the temperature, and that the temperature follows an Orchan-Uhlenbeck, where μt is a kind of deterministic seasonality term. This is essentially the flavor of our underlying model in what follows. So the risk, of course, since capital L is a loss, we want to measure the risk induced by L in a disymmetric way. So we'll, of course, think about the value at risk or the conditional value at risk at level alpha. You have many other risk measure in the same family or even from different family, but when you work with practitioners, you can easily work with value at risk, but even conditional value at risk becomes challenging if you want to convince them to use it. So as everybody knows, the value at risk at level alpha is the alpha quantile of the distribution of L, and the conditional value at risk is the induced mean loss given the fact that the loss is greater than the value at risk. So we have this well-known but very useful for our purpose proposition by Rockefeller and Uriasev, which is a representation of the conditional value at risk. But this representation is not the canonical representation of risk measure over the dual representation of risk measure over all the probability, the martingale probability. So this is a specific one, which says that the conditional value at risk is the infimum over all xi on the real line of this function, which is xi plus 1 over 1 minus the level, the confidence level, times the expectation of the positive part of capital L minus xi. And this is a convex function that goes to infinity as xi goes to plus or minus infinity. So there is a minimum. This function here has a minimum, and you can show easily that this minimum xi, this arg minimum xi star alpha is simply the value at risk, and as we define here, the infimum of this function, the minimum of this function in xi is the conditional value at risk. So we can represent, in some sense, the conditional value at risk as the infimum of an expectation. And if you have in mind to implement some stochastic approximation algorithm, for example, it's crucial to have that the function you want to minimize is an expectation. So you know also that conditional value at risk is known to be a coherent risk measure. It's subadditive, positively homogeneous, invariant by translation, and monotonic. What we need for that, for our purpose, was to extend that to dynamic risk. So we introduced, but not really introduced, it's very natural, and we don't claim we are the first to do that, of course, a conditional CVaR. That means that we assume that the loss has a finite conditional expectation given the observation up to L. And we consider that the GL conditional value at risk is a random risk measure defined as before, except that now it's not an infimum but an essential infimum over not all the real xi but all the random variable xi, which are measurable with respect to the information available at time L. But for the rest of it, it's exactly the same. Of course, the expectation has been moved to a conditional expectation. So this is still random, except it is random, it's still a coherent risk measure. And you can note that this quantity, as L varies between 1 and m, is a super martingale. That means that the risk has a trend that a decreasing trend as time increases. That means that, of course, at time L equal to m, at the last observed time, the risk is just equal to L. Okay, that's maybe the point which is not, which is, let's say, a bit more original since the beginning of the talk, is that we were asked not to use the conditional value at risk as a criterion, that means as a constraint, that means to hedge with respect to a constraint involving the conditional value at risk, but to directly use the conditional value at risk like the square of the norm. You see, if you do some quadratic hedging, that means the direct criterion that we want to minimize to produce this hedging. So to reduce her risk, the portfolio holder uses a dynamical self-financial strategy, as usual, adapted to the observation. So you have, with a null initial wealth, this value for the portfolio. That is completely elementary. And we want to solve this. That means among all this hedging portfolio, we want to minimize the conditional value at risk over all this strategy. So the first step to the solution is, of course, to deal with the one-step partial hedging. That means that we will specify an instant L0 and we'll forget about all the others. So we have time 0, time L0, and the terminal time capital M. So the gain resulting from the strategy theta, which is 0 except at time L0, is of course theta L0 time xm minus Lx0. And at this moment we have two natural problems that can be solved. The first one is to solve, of course, the minimization problem related to the CVaR, like that, which is in some sense the static risk, the hedging of the static risk. And you can also look at the hedging of the forward risk. That means that you look at the conditional value at risk given the information available at L0. So you compute this random risk measure, and then you take the expectation to see what is the mean risk view at time 0 of what you have of your minimal risk at time L0, given the information at time L0. And of course you want to minimize all this over all the possible hedging strategy at theta L0. Okay, so we have three problems: two one-step problem and one global problem. The existence of optimal solution is a very classic, is again rather classical. That means, of course, we set x is equal to xm minus xl0, and we assume that there exists a regular version of the conditional distribution of the couple L, the contingent claim, and x, the price increment, given the information at L0. We denote it p omega dy dx, and we assume that the loss is integrable, that x is integrable, and what is more, x, let's say, has a density, and we also assume that it is a martingale increment, and this L1 ellipticity assumption, that means that the expectation of x projected on any direction, the positive part of this quantity, is always strictly positive over when you should ask also u to be of norm 1, otherwise of course you take u equals 0, it doesn't work, so you must ask norm of u to be equal to 1. So it's the L1 ellipticity. And then you consider the Rockefeller-Uriasef function here, small v of psi theta yx, and you integrate it with respect to p. And you can show then that under this assumption, the static problem and this forward, so the static problem here and the forward risk problem here, both have solutions. That means that you can find a quantile in R and the strategy at L0 for the first problem, or here random quantile, because you first solve this GL0 CVaR problem, and an optimal strategy that minimize problem 2 and problem 3. So the argument is the canonical bifurcation property from stochastic control. That means that you can interchange the infimum over all the possible strategies at L0 and the psi, which comes out in the definition of the conditional value at risk. And then once you have interchange, you can compute this essential M-inf using a kind of Markov property given by the conditional distribution. This essential inf is the minimum of this random function, and this random function for every omega is convex, Lipschitz continuous, even differentiable. So it attains a minimum, and this minimum is the solution of the optimization problem inside the expectation, and then you take the expectation. It's still Lipschitz, continuous, convex, and goes to infinity at infinity. So you need some uniformity in theta here, and you have the existence. So it's rather standard argument from discrete time stochastic control. As concerned the first problem, which is the most interesting one, in fact, you can, again, using bifurcation argument, deal this dynamical problem by decomposing this problem in two sub-problems. So you have the infimum over all the admissible strategy, and you can consider that you can interchange the expectation and the infimum over xi. I remember you that this CVaR is defined as the infimum over xi of the Rockefeller-Uriasef function, and then you have to solve this problem over all theta, admissible theta, and of course we consider that xi is first fixed, and we solve first this problem, and this can be done using still the same argument. That means that the distribution, the whole distribution is integrable of the increment on L, and then you have a martingale property for delta. This is not completely correct. That means that for every L, not L0, you have this L1 ellipticity, but for you having a norm 1, of course, which is not written once again. X is a martingale, the price is a martingale under our probability. That's the main restriction of our work, but that can be removed, but I won't speak about that today. So you have an existence of a solution, so it's once again classical argument using the Bellman function and the backward induction. But this backward induction is not natural. The Bellman function do not correspond, like for example in optimal stopping, to the backward solving algorithm of the problem. But in fact it provides the existence of a solution. So now we can think about the evolution of the risk of the hedge portfolio, and what you see, it's very easy to see by a measurability argument. You see that the sum from L equal to 1 to up to K of this quantity is GK measurable, and on the other hand, it's a super martingale. We know that from the beginning, because you put anything here and you have a super martingale up to integrability assumption. So this quantity is equal to the value of the portfolio at time K plus the GK conditional value at risk of L minus the remainder, in some sense, of the portfolio. So that means that the estimate of the risk of a hedge loss does not depend upon the past. That means you have a kind of Markov property for free. If you want to solve this problem has been already solved. At time K, you just have to solve this one. So the past is not involved in the solution. So now we can pass to the numerical methods. So what we choose to do, but that could be, and that can be, and I hope it is sometimes, a generic method to solve some stochastic control problems, because at each step in a stochastic control problem, you have to do some optimization, and this optimization most of the time appears as the infimum or the maximum of a function, which is the expectation of another function. So in this case, you can always introduce a kind of stochastic algorithm. So I will try to, if I have time, to explain you how to proceed. So our work to solve if we want to solve the problem 3, for example, the hedging of the forward risk, we consider that X is a GP martingale, the filtration of the observable, and we also assume that XZ is a Markov chain, very classical. So it's a one step. It's a one step. So the increment between L0 and M depend on L0 of X and Z, so the price and the temperature, and some innovation. And L is a function of the same for a function F. Okay, so the fundamental result for solving the problem is once again to introduce V, which is the expectation of the Rockefeller-Uriasef problem, but now with this quantity instead of L. So here, and then we consider the infimum of this quantity, and once again we can interchange inf in essential inf, and so we can see that it is the expectation of this quantity here, and this quantity inside can be computed. In fact, this quantity is the minimum over psi and theta of capital V of psi, theta, x, and z, which is where it is, which is this quantity. So we have to minimize the expectation of a function which depend on x and z. So you can imagine a cubature formula. I will come to that in a minute, which will say that if you have some weights, you can compute this expectation using a grid. That means that we consider several value of x and z, and we assume, for example, that it's an optimal quantization grid. That means that we have x and z, and we consider some points like that, and we assume that, of course, Wj and the direct mass at xj, zj is a good approximation of the law of x L0, z L0. You can put L0 here. And so, of course, the expectation of f of x L0, z L0 is approximatively this quantity, if f is reasonable. So that's what we use. It's like for any cubature formula, but the difference between quantization and other method is that we have a very good idea of what are the mass. That means that Wj is the probability that the couple x L0, z L0 belong to the Voronoi cell of xg L0, zg L0. That means that you consider the mass for the law of the couple of this area, and you consider that it is the weight. So of course you can compute all that by a Monte Carlo simulation of all these weights and even the points using a clustering algorithm. So this quantity can be made available rather easily. So how to proceed now? Because we switched from a global problem. We switch from a global problem to a local problem. Now we just have to compute this quantity at a given point, xj L0, zj L0. So it's of course much simpler. On the way we lose some, of course we had some errors, but there is no way out anyway. So we have to solve this local problem. So what do? We first compute the gradient with respect to psi and theta of this function capital V psi theta. So you can write that it is the expectation of h1, h2, d plus 1, where h1 and h2, d plus 1 are this function. This is clearly the function corresponding to the quantile search, and this is the function corresponding to the hedging portfolio. And one compute online, furthermore, the minimum, that means the conditional value at risk, by a well-known companion procedure, which is Cn is equal to Cn minus 1 minus gamma n, Cn minus 1 minus this small v function. The small v function is all this quantity here. So you have this algorithm, which is a classical stochastic gradient. That means that xn theta n is equal to xn minus 1 theta n minus 1 minus gamma n times the local gradient. That means the quantity which is inside the expectation and which gives after the expectation the true gradient. So this is very classical in stochastic approximation, which is a very old story going back to Robbins and Monroe in the 50s. essentially to compute quantiles at the origin. So what is interesting is that under our assumption, you can prove that psi n, theta n, and Cn converge toward the conditional the value at risk at our point, the hedging strategy still at this point, and the conditional value at risk still at this point. And furthermore, it satisfies the central limit theorem at rate square root of n if you have selected gamma n as small c, a constant to be specified, over n. In fact, there are many other problems and things are not so easy, but under appropriate assumption, everything goes well. So now we want to conclude by by solving the original problem. But of course, the original problem, if you want to solve it directly using the same kind of method, you see that the dimension of this problem will be m times d times the number of assets. It's d is the number of assets. So it's m times the number of assets. It's even more than that. It's not reasonable because you are facing the curse of dimensionality. As soon as you use a cubature formula somewhere, you face the curse of dimensionality directly if you use quantization. And for example, if you use some cubature formula at the Lyons-Victoire way, you have an explosion of the number of points. So whatever the method you use, you have a problem when the number of assets increases. So the idea is to use a suboptimal, well, maybe I won't speak about that. Yes, one idea is to propose an approximate solution. The first idea is to decompose the loss as the sum of its martingale increment. That means, in some sense, compute all the European options related to L. And you can show that our problem, our target problem, global problem, is lower than the expectation of L plus the sum of this local problem, local in time, but involving only one term of the hedging strategy. And this is due to the subadditivity of CVaR. And finally, you do something which is strange. Since you made an upper bound here, now you lower bound this static CVaR by the forward CVaR. That means this quantity. So of course you have an upper bound here, a lower bound here. So we don't. It's an approximate solution, but we don't know exactly if you compute an upper or a lower bound. Sorry. So in some sense, with all what we did, you can compute this quantity. In fact, this quantity is exactly what I described during my when I make some schemes on the blackboard. So it's possible to compute that by quantization, for example, and so you can produce some result. I want now. Once you have done this, you can put it in a computer and it will work, except that, of course, usually you have alpha very close to 1, and all our algorithm, of course, essentially the quantile search, doesn't work very well. It's very slow and chaotic as soon as alpha is very close to 1. So you can use, you have to use some recursive importance sampling method to modify your stochastic algorithm. So I did that with Vincent Lemaire in 2008 for general stochastic, more general stochastic algorithm. So you can implement that. It produces 2 more companion components to your algorithm. So it becomes a big, very big algorithm in terms of dimensionality. But you can, doing that, put some light where you are interested in the event you are interested in, as you usually do with importance sampling. You can also add some linear control variate, since when X is a martingale, of course, you can very often use some, if you have some closed form for delta XL, for example, for the expectation of function of delta XL, or equivalently, if you have some closed form for the European options related to your payoff L in this formula, here, you can use them as control variate. Okay, so I wanted to show you now what you can do numerically. So you imagine that you have a gas supplier that buys on the spot market an immensity of gas at price S gas capital T and sell to its client at the regulated price capital K, because in France the price of gas is regulated price. Of course, for people from abroad maybe it's not obvious, but to French people it's obvious, historically speaking. I don't know if it will last. Okay, this quantity is the consumption, and we stop at time t is equal to 1. We consider that, of course, we will transform this problem into a discrete time problem, and so we model the temperature by this discretized Orchan-Uhlenbeck process at time 1, but it's an exact discretization. And we consider that the two Brownian motion, the one for the price of the gas, which is a geometric Brownian motion, and the G1 here are correlated with rho is equal to minus 0.8. And I just wanted to show you what it makes. That means here you have, for example, the histogram of the loss without hedging in solid line, and then you have what becomes the distribution of the loss after implementing our algorithm. In fact, it's the last one, the one which is a strange approximation. First you upper bound, then you lower bound, which is not rigorous in the mathematical term, of course. But what we want is to reduce this risk. So you see that the high value of the loss have the tail is less heavy, of course, and you reject, of course, the mass here. So, of course, also you have less loss, but you have less gain, because here the loss, it's a loss, so you lose money here and you win money here. And of course, if you reduce the loss, you reduce the gain. And you see, although it is dissymmetric, that means that the distribution is more close to its mean, but not in a symmetric way, as you would do with a variance criterion. So I have no time to make the comparison. In fact, I have no slide here to make it. But when you do something with quadratic hedging, of course, it's much less efficient, because you can keep more gain, but in fact you reduce less the loss. And what was the main concern of GDF Suez was to reduce the loss. It seems that they have other way to win money. Thank you very much.
You were assuming X as a martingale. Why can we do that?
That's in fact that's the assumption of the company. The X is not the spot price of the gas; it's some future contract, and they consider that they price it under the risk-neutral probability. That's their assumption. But I have no time to explain. But in the paper. And in the second paper made by Frikha alone, we deal with the case where X is not a martingale. But it was easier to explain here, not taking care of the conditional expectation of the increment. But of course, on energy markets, this assumption is highly questionable. But on the other hand, well, this work is 3 years old, so maybe things has changed now. But 3 years ago, at least in GDF Suez, this assumption was in course. But I agree it's questionable, because I have long discussions with the management in GDF Suez. But that I have just an opinion, you see.